So the last thing that we have discussed last time has something to do with the so-called working electrodes. And here are some of the examples of the working electrodes that we have. So I already told you this is your dropping mercury electrode, the hanging mercury drop electrode, and then this is the solid disc electrode, the micro electrode, and this is the one that I told you that is common nowadays, especially for portable stuff, the so-called screen printing electrode. So as you could see here, so the size of this is just maybe like this one, okay? And you're going to put the clip here of the electrode system, and you will see here you have the working electrode, the reference electrode, and the counter electrode, okay? So that's how small the what we call the analysis that can be done now. And all you need to do is drop your sample around here, okay? And you can do the analysis in terms of this, what we call the working electrode. Now, what we usually do in this type of, we could say, working electrode, as I've told you, based on the unpublished papers or thesis that I gave you, most of them is the fabrication of the working electrode. So the common lead that we use there is the so-called carbon-based electrode. So in the screen printing electrode, you can use a carbon, or they put it like a carbon ink, okay? So they mix it and then they dry it there, okay? And then they put some materials that they have there for you to be able to use it as a, what we call 3-electrode cell, okay? See, Ma'am Leah has this type of working electrode there in UPLB. And if we're going to look at this working electrode, we can say that we can venture to this so-called modified working electrode. And this is really an active area of research in electrochemistry. And that's what I did, if I'm not mistaken, 20 years ago there. Okay, the development of electrodes produced by chemical modification of various conductive substrate. So these electrodes, they have been tailored to accomplish a broad range of functions. And you can do some sort of chemical modifications on these electrodes. So one way that they look is the so-called chemical modification. So among these chemical modification is the irreversibly adsorbing substances. So look at the word here, adsorbing. Okay, so it would we could say application of irreversibly adsorbing substances with discharged functionalities. So ano ibig sabihin nito? Okay, so what is the difference of adsorb doon sa absorb? Anyone?
Adsorb po nasa surface lang yung particle, and then absorb po is yung mag-i-insert talaga siya dun sa loob ng
Okay,
substance.
so absorb is, we could say, internal, right? This one is more on surface. Tama ba, Judy?
Yes
Is
po,
that what
sir.
you mean? Okay. So the way that you're going to look at this is you're going to find some substances, okay, that when your target analyte or any analyte you want to bind it, okay, react with it, there's what we call like adsorption that is happening. Okay, and it's hard for it to be removed. That's why irreversibly. Okay, so once it's absorbed, it's stick there. Okay. So another way of doing is we could say the covalent bonding. Okay. So maybe one example that I will show it to you here is the what we call this one in the absorption. So we have here the so-called oxidation of the electrode. And this oxidation can either be a metal or a carbon surface. So what does it do? Okay, it oxidize your metal or your carbon, giving you either an OH group or an oxide group. Okay, so the way that you do this thing is, we could say, electro deposition. So that's one of these what we call irreversibly absorbing substances that can be done. You have a metal, okay, that can have absorption there. Okay, and they have utilized this thing where the functional groups are formed when your metal or carbon surface are oxidized. So what could be the oxidizing agent that you can do it? Either an oxygen or any other stuff where you can apply electricity, or we could say electrochemical technique to oxidize it. So you can also use bleach, any oxidizing agent. Okay. So the other thing that we have, we could say, is the covalent. Oh, before that we go there, in terms of carbon, this is how the oxidation would look like. So you have like carbon here, and then you oxidize it, you form an alcohol or carbon dioxide, or you can have a carboxylic group here, or you can have here, ano ba tawag dito? What do you call this? Ester?
Ester group, sir.
Huh?
Ester.
Ester? Hindi kasi ako orgo eh. So what happened is you can do this one, okay, to modify the surface that you have there. So this is, we could say, example of modification. Okay. Now you can also do covalent bonding of the components. So here you can have what? SAM. You're familiar with SAM? Anyone? This is we could say a big field in chemistry. Anyone? Any idea what SMM mean? SAM? Class? What does SAM mean?
S-adenosylmethionine po.
Okay. So usually what does it do?
For methylation po.
For methylation. Okay. So as I've told you, this is a very, we could say, big field in chemistry. So sometimes just with the what we call glassy surface, they can what we call do some modification. Okay. SAM is just what? Sub-assembled monolayers. Okay. So what it do is really targeted the software, the surface in this what we call doing. Okay. So that is an example of covalent bonding. So the SAM usually they use what? Thiols with amine and carboxyl or carboxyl. They can also do organosilane. So organosilane is just this one. This is usually the one that they do in what? Sol-gel process. Okay. Or they can do coating of the polymer film. So they can use here what? Spin coating, deep coating. So among the stuff that they can do here is maybe this one. Okay, so if you're going to look at here, what happened here? There is an SiO, a silane. So we could say there's a linking agent here that is made up of the organosilane, okay, bonded to the functionalized surface. So this is the surface that you have. So when you have that, okay, you can modify the stuff that you have. Or you can have a graphite here. And what you do is you're going to attach this thing with, what is this? What functional group is this one? CO, carbonyl group, okay? Or we could say amine ba or amide, okay? So there's an amide group that you have here. So you can make some modification by attaching it, okay, in a graphite electrode. So if I'm not mistaken, this is a pyridine ruthenium stuff that you can use. Now, if you read already the papers or the thesis given to you, do you think we did chemical modification there? Yes or no?
Yes, sir.
Ha? May chemical modification ba dun? Ha? If you say yes, anong chemical modification doon? Anyone? You see na nagsabing yes. Because what I know is we didn't do any chemical modification there. What we did is we just mix the modifier, as we call it, with the carbon paste, hoping that it will serve like as a binding component. Okay. So when we apply the potential, what happened is any metal ion will be reduced to become metal. And that's the one that we're going to monitor. Because if you're going to look at the current that we try to analyze there, current is just the electron flow. Or current is the result of the electron flow when we applied potential, okay, to the given system. Now, in terms of the applications, where do we utilize usually this one? You can utilize it in electrocatalysis. Okay, so there are many applications of these so-called modified electrodes. So primary interest that you have here is the so-called electrocatalysis. So what usually you have here, you have electrodes where are they capable of reducing oxygen to water? Okay. What do you feel, what field do you think this is being used? Where electrode is capable of reducing oxygen to water? Usually that is in the fuel cells industry or the batteries. Now, another application of this, we could say modified electrodes is this what? Smart window. Okay. So the one that you're taking advantage here is the so-called electrochromic. So what does it mean? Electrochromic devices. What does chromic means?
Colors po, sir.
Colors, okay? So what you do here, you're developing electrochromic devices. So what it do is, when it undergo redox reaction, okay, it can change color, whether it is oxidized or what we call reduce. Okay, they utilize now some of this what we call smart window. Sometimes what they do, depending on the temperature, the window change color. Okay, so that it will not be hot to the eye when let's say the sunlight becomes so bright. Okay, but in terms of modified electrodes, what you do is you put these electrochromic devices, okay, that change color upon oxidation or what we call reduction. Okay, you always call it like a smart window or smart mirror. Now you can also use electrochemical devices for this what we call the molecular electronic devices. So that's where we call the e-nose, electronic nose, okay, electronic tongue, and other stuff that mimics the senses that we have. So typically we could say they take advantage also of the redox reaction. But the one that is applicable to us and the paper that you're going to write is analytical sensor. That's the most important analytical use of electrode. And they're taking advantage here of a particular species or functional group. Have you identified what functional groups your modifier has?
Yes, sir.
Sige nga, isa-isa tayo. Sabihin niyo yung modifier at ano yung functional group niyo. O anong functional group meron yung modifier.
Yung sa akin po, sir, is yung modifier po na ginamit is 16 with the
16. So that means you have what?
thiol po na functional group.
SH. So you can look at the what we call the interaction of the so-called sub-hard metal with this sulfur containing functional group.
Sir.
How about yung iba? Para may idea kayo kung ano yung hahanapin nyo. Judy.
Sa akin po, sir, ay white lahar po yung ginamit. Pero hindi
shoot.
ko pa po nababasa kung ano yung functional group. Kasi medyo, ano po, complicated yung composition.
You know Dr. Sabularse?
Yes po, sir.
They use lahar as a column material tapos nilagyan nila ng invertase, I think an enzyme.
Mm.
Okay, but lahar itself, because what happened is it depends on the lahar, and I think we put some of the functional group, because this
Ah, yes
functional
po.
group will be the one that will interact with your
Mm-mm.
heavy metals. I'm not sure if it's silicates.
Meron siyang SiO2, meron ding, madami po siyang
But
composition.
basta, I think we put something there.
Yes po. Pero specific lang po na white lahar yung ginamit. Tinanggal po yung black lahar. Yes.
Because I think they treated it with an acid, some sort of.
Yes po.
Yeah.
Dinisolve po siya and then tinwrite, tas saka po minix dun sa ibang components ng electrode.
Yep. Because the idea there, if you add an acid, it could serve like a cation exchange. And we target a cation like lead 2+. So that's the principle that we're trying to look at it. So ganun yung magiging ano mo doon. O yung iba, para alam niyo paano yung starting point niyo. Wala na iba. Sino yung dito yung mga prutas?
Yung sa akin, sir, ay garlic po.
Garlic. Yung masamang amoy ng garlic, I think it's a sulfur. I'm not sure if
Opo,
garlic contains
allicin.
allicin.
Apo. Yung nakalagay po sa kanya, allicin po na may disulfide bonds. Yun.
Oo, kasi allicin, I know it more on onion. Okay?
Opo.
But I think that's also what they put there. Because originally, onion yung ano nila. Sabi nila, sir, maluha-luha na nga sa thesis, gagawin pa natin literal. Kasi the olfactory thing on onion makes you cry. So sabi nga nila, sabi ko, ako nga, dugo literal ng MS thesis ko eh. Because I work with lectin. So one way to look at it, to see the agglutination is you have to test your blood. So I always go to infirmary or the university health service. Tapos dala-dala yung test tube. Sabi ko, oh, paano ho? Pakuha ho ng dugo. So, and then after that, we use it. Okay. So ganun yung when we literally says, dugo at pawis yung puhunan namin sa thesis. Sabi naman yung isa siya, sir, huwag na mag-ganon. Okay. Naluluha na nga kami sa thesis, paluluhain niyo pa kami. How about the others? Sino dito yung, ano ba yun? May pipino throat ba? Hindi ko kasi alam ano yung na-assign sa inyo eh. That's why I'm
Akin-
trying to... Okay, siya, Jan.
Akin po, sir, apple.
Apple. So, ang apple ay nagiging brown, di ba?
Yes po.
So, ano yung, ano doon? I'm not sure if it's phenol oxidase. So, you have some biological enzyme there.
Opo, tyrosinase.
Tyrosinase? Yeah, yun, mga ganon. Yun lang yun eh, tinitake advantage natin sometimes kung ano yung biocatalysts or enzymes that they have. That's why we chose them as the so-called modifier. And some I think are literally what? The amino acid. Meron ba ditong amino acid aside from cysteine? May nakakuha ba ng methionine? Because kung ano man yung function. Sa'yo yung gene, methionine?
Apo.
So at least you expect there to have amide and the carboxyl group. So meron talagang tawag dito reason why we choose those modifiers. And the thing is you take advantage about that. So ano ba yung interaction nila with metal? Ganon yung ano namin doon, yung pag we could say attack sa problem. Okay? Now, in all of these what we call voltammetric analysis that you do, you always have this so-called potentiostat. So usually that's the voltage source that drives the cell. So I'm showing you here the potentiostat that I have in my lab. So this is the bench lab. And if you ever see that one, like the alligator chip, so that's the one that we use to attach in this one. So kasha yung alligator chip dyan, or alligator clip dyan to hold them together. Okay? So this is the bench top. And this is what we call the portable. Yung metro. So this is BASI. Bioanalytical System Incorporated. And then this is Metrom. So sila yung, we could say, the leading company in doing electrochemistry stuff. Now, what the potentiostat do, it supplies whatever energy needed between the working electrode and the counter electrode to maintain the specific potential between the working electrode and the what we call reference electrode. So it's usually a very high impedance so that the current passes through the reference electrode is minimized. So kailangan usually yan, okay, sa system. Siya kasi yung, di ba, ang voltammetry is we apply potential and see what's the current that we'll get. We measure the current as a function of the applied potential. So diyan yung parang source ng potential mo. Okay? And the way that we apply potential, we could say is time-dependent potential to an electrochemical cell and measure the resulting current as a function of that potential. Okay? So this is the one that the owner of this is really the Republic of the Philippines. So I'm just trying to return it. Unfortunately, yung main collaborator ko passed away. So, and hindi naman chemistry yung field niya. It's really food science. So, that's why I think I want to house it to someone who can do and utilize it in chemical fields. That's the reason there. Kasi wala naman nagamit ng mga bata. They don't want this one. Okay, they just want the spectroscopy or chromatography. Kasi yun yung uso dito sa industry. Okay? Now, let's look on this what we call a typical voltammogram. So this is, we could say, the appearance of a typical linear scan voltammogram. Okay? So if we're going to look at this linear scan voltammogram, okay, look at the wave. Anong masasabi natin dito sa wave na to? Sigmoid ba yan? Is that a sigmoidal shape? Okay. So if we're going to look at this one, it's a sigmoid shape wave of what? Potential versus the current. So if you're going to look at this, this is a measurement of current versus the applied voltage. Okay. Now, if you're going to look at the analysis, this is really what happened. You have an analyte, okay, that gains electron to give you a product. So what is this? Ano sa redox to? This is
Reduction.
Po.
reduction. Okay? So what happened here, if you're going to look at this, there's an increase in the current at potential at which the analyte is reduced. And for this to happen, you need what I showed you earlier, the potentiostat. Okay? So the potentiostat provides the electron. It provides the energy that you have there. Okay? Now, if you're going to look at the half-wave potential here, as you could see, it's close to the zero potential or zero current as you have here. Okay, as the zero potential, you start here. Okay, so this is in between. So if you're going to look at the E1/2, the potential of 1/2, so it is what? The reduction potential that you have minus the reference potential. And since this is 1/2, which is just 0.50, so we could just say whatever the reduction potential minus 0.24. Okay. And if you're going to rearrange it, this is the potential that you get. So if we're going to look at here by convention, what can we say? This one, the reduction current is, if you're going to look at it, it goes up to positive. Okay. Now, by convention, the so-called cathodic current, because that's where reduction takes place in the cathode. So the cathodic currents, they are taken as a positive sign. Now, the oxidation current, which is the anodic current, on the other hand, is assigned with a negative sign. So we could say, by convention, the cathodic currents are positive and the anodic currents are what we call negative. Because sometimes before, iba yung European way, iba yung American way. And I think in some of the old people are still what we call having that confusion that you have. Now, what can we see here? We have the so-called limiting current. So what can we say about this limiting current? So if we're going to look at this, ang tawag natin dito, although we call it linear scan, but this is what we call a linear sweep. So what we do, we apply a potential, so from 0 to -1 volts, and see what happened to the current that we have here. Okay. So this is what we call the voltammetric waves. Now, this constant current that we have here, okay, beyond the steep rise, ang tawag natin dyan, limiting current. And they said this is a diffusion limited current. Why do you think there's the term the diffusion?
Kasi dependent po sir sa concentration po.
The concentration due to diffusion is one of the what? Ano yung tawag natin yung sa tatlong term? Diffusion,
Mass flow po.
convection,
Sport.
okay? The mass transfer, right? So we could say here, we call it a diffusion limited current or just limiting current because the rate at which the reactant can be brought to the surface of the electrode by mass transfer, okay, is due to the diffusion. So the limiting current here, we could say, is proportional to the analyte activity. So kapag madami yung analyte mo, ano mangyayari dyan? Mas mataas yung current mo. Look at here. Okay, so that IL that you have there, that is proportional to the concentration of your analyte. So limiting current, we could say, are directly proportional to the reactant concentration. So we could say we can use this for what? Quantitative analysis. In fact, this is the simplest voltammetry. Okay. Now, the potential at which the current is equals to 1/2 of the limiting current, ano tinatawag doon? Yun yung tinatawag natin half wave potential. And you're given the symbol E 1/2. Okay. So this, we could say half wave potential. This is obtained after correction for the reference electrode. Okay, the half wave potential, it's closely related to the standard potential for the half reaction, but it's usually not identical to it. Okay, closely related, but not identical. So it's relative to the reference electrode, but that can be used to identify a particular substance. Okay. Half-wave potentials are sometimes useful for identification of the components of a solution. Now, as much as possible, you want, okay, your limiting currents to be what? Reproducible. And you can achieve it. How? Okay, you can achieve a reproducible limiting current rapidly when either the analyte solution or the working electrode is in continuous or continuous and reproducible motion. Okay, so that makes this what we call linear sweep electrode, the one that what we call the hydrodynamic voltammetry, which we're going to discuss later on. But that's only applicable if it's continuously, we could say, in motion. Now, if we're going to look at a typical LSP, linear sweep voltammetry, so a specific example that we have here is the cadmium. Namove yung cadmium. Undergo cadmium 2 plus being reduced to cadmium metal. So the potentials applied on the working electrode is usually swept over or scanned. So you have a predefined range of applied potential. So you will be the one to set it. Okay, so as you see, becoming more negative, so that means you're applying potential to it. So if you're going to look the anatomy here, so at the beginning, the working electrode is not yet capable of reducing cadmium 2 plus. So you only have small residual current that flows through the electrode. And then what happens when it starts to go up? The current starts to be registered at the electrode. Ano ibig sabihin yun? Meron ng nag-form na cadmium na nag-attach doon sa electrode. Okay? And then, at this potential, 0.6, which is your halfway potential, the electrode become more and more reducing and capable of reducing cadmium 2 plus. So, mas dumadami na yung cadmium na nagpo-form. Okay? So here, the current at the working electrode continue to rise as the electrode becomes more reducing and more cadmium 2 plus around the electrode are being reduced. So diffusion of cadmium 2 plus does not limit the current yet. And when it comes here, what happened? Nagpa-plateau na. All the cadmium 2 plus around the electrode has already been reduced. So current at the electrode becomes limited by the diffusion rate of cadmium 2 plus from the bulk solution to the electrode. Thus current stop rising and levels of at a plateau. So this is now your limiting current. Okay. You can also see here the baseline of your residual current. So this is, we could say, the anatomy of an LSB, a linear sweep voltammogram. Okay. The question so far, we didn't do that in the thesis that we have. What we do is like a pulse and CB. So yun yung papabasa ko sa inyo. I have an experiment about this in your college, and I'm trying to do it at Pace University kasi nandoon yung tinatawag natin mga potential stat ko. Because what we have in your college is an old model, analog potential stat. So hindi ko pa nagagamit kasi it's just I don't know how to operate that thing. Is older than the one that I'm using when I was there in UPLB, yung sa Metron. Metron din yung nasa UPLB. Metron Voltammetric Analyzer. I don't know if it's still working doon sa Earth. Or I forgot the room. A3 something. Okay? Now, let's look at the so-called circuit model of a working electrode. So when we're talking about the what we call circuit model, it's just useful and instructive to represent the electrochemical cell as an electrical circuit that corresponds or responds to excitation in the same way as the cell. So if you're going to look at these electrodes, so this is what you have. So you have the electrode, the double layer, the diffusion layer, the bulk electrolyte. So this is not new to you. Okay? We have discussed this before. So we could say this is the electrode that you have. So you have a double layer one. You have the electrodes on the one side and the other one, that's where the analyte meets the surface of your electrode. So if you're going to look at this one, we assume that this electrode is your what? Working electrode. Okay. And we also assume that your counter electrode, it has a large inert electrode that it is, we could say, non-polarizable, and that it serves only to make contact with the analyte solution. So what I will show you here are the schematic of the of a number of possible circuit models for the electrochemical cell. Okay, so the first one is what we call the Rundle circuit. Rundle. So what do we have here? So what do you think this one? What does R represent? Resistance. And that is connected here in terms of what? Solution. So a Rundle circuit, it has a solution resistance. Okay. And then we have here a CD. So we can call the CD as what? If you're going to look at this is the diffusion layer, or what we call the double layer capacity. Okay, so this is the one that we have here. So what do you think is the CF here equals here? Anyone? That's the Faraday impedance. So these are, we could say, the main component of your Rundle circuit. Now, as you could see here, the solution resistance and the double layer capacity, they represent the behavior of real electrodes quite accurately over a broad frequency range, and their values are independent of the frequency. The Faraday impedance does not. Okay. Now, compare it to the next one. So what's the difference of this compared to the first one? Anyone? What's the difference of this one compared to this one?
Yung ZF po?
You have a CS. What else?
May additional rin po siya na resistance, yung RS po.
RS. Okay. So the component that you have here with the same symbols, that's the same, we could say, component as you have in the Rundle's one. Now, in the second circuit, okay, the RS that you have there, that is the resistance from, sa tingin nyo saan? Electron transfer resistance. While the other one is a capacitance, but this is what we call a pseudoscience or pseudo capacitance, pseudoscience. And this is due to what? The mass transfer. So what happened here? You're applying a small amplitude sinusoidal excitation signal to a cell containing this type of working electrode. And it is assumed that the value of the applied voltage is insufficient to initiate the Faraday process. Kasi wala yung CF, di ba? Wala yung Faraday impedance. Okay? So, what happened here, your double layer capacity, it acts as a short circuit. So if you measure the peak current here, you find that the solution resistance here is equals to the voltage over the current. Now, the difference of this circuit model compared to the first one, you can isolate this circuit and their values determined using the alternate current circuit measurement technique if you want to isolate them. Okay? So yun yung difference nung second one doon sa first one. Now, the last one that we have is this. So what's the difference of this with the other two?
Yung ZW po.
The CW. And we call this CW as the so-called Warburg impedance. Okay, and then we also have RCT. So anong resistance to? So we have CT there, so we could call it as the charge transfer resistance. So here we could say the Faraday impedance is represented as the series combination of RCT and CW. Okay, now this charge transfer resistance, this is given as RCT equals to the overpotential divided by I. The overpotential for the Faraday process at the current, at the working electrode divided by I. Okay, so I is your current. Now the Warburg impedance, on the other hand, we could say that's a frequency-dependent circuit analog of the resistance of the working electrode to mass transport of analyte molecules across the electrode solution. So this is, we could say, the three common circuit model of the electrode. Now, with modern technology, computerized frequency analysis, instrumentation, and software, it is possible to acquire impedance data on cell. Diba, one of you worked with impedance stuff before? Am I right? Si Jean ba yun? Ano yung in-analyze nyo sa impedance? That's Jean. Jean? Yan ba si Jean? Ano yung ginawa mo, Jean, sa impedance noon with Sir Alvin Tapia? Away ata. Usually when you have an impedance thing, you apply an alternate current to it. I'm not really, we could say, familiar to it. Okay, but usually the one who do that is in physics. The physics, if you can fabricate your some of the what we call materials there, sometimes you can build your own potential stat, then That would be low cost instrumentation. Okay. Now, this brings us to the so-called hydrodynamic voltammetry. So when we're talking about hydrodynamic voltammetry, so if you're going to look at the wordings there, what's the main wording here? Dynamic. Okay. So typically, in hydrodynamic voltammetry, it can be performed in several ways. In one way, you have a solution that is stirred vigorously while it is in contact with the fixed working electrode. So merong stirrer that is installed there. Sometimes it's the working electrode that is being stirred. Yung umiikot siya, especially if you have this electrode, the so-called rotating this electrode. Okay, so the typical cell for a hydrodynamic voltammeter is this one. So you have a counter electrode here, a reference electrode, and you have a working electrode. Now this one is used for what? Purging. Okay, so you have a salt bridge. So sometimes if your reference, your working electrode is not rotating, you can put a steering bar there. So you can have a steering solution. Okay. So whenever you have a hydrodynamic voltammetry, this is a type of voltammetry where the analyte is kept in continuous motion. So if you have a continuous motion here, that means there's really mass transport. Okay, and you still recall what are this mass transport, the movement of material toward or away from the electrode surface. So it can include what? Diffusion, migration, and convection. Now, the one that is common here, diffusion, which is the movement of material in response to a concentration gradient, and convection, the movement of material in response to a mechanical force, which in this case is steering. So remember, diffusion limit in the LSB that we have discussed. Now you may ask, why is migration not there? Anyone wants to answer? What do you need in migration? Anyone?
Charge potential, sir.
Charge. But what do we do in voltammetry? Why do you think migration is not involved here? How do we prevent in voltammetry migration from happening? Even though we said we apply charge to it. So ano yung pumipigil? Anyone? In supporting electrolyte. We attempt to minimize the effect of migration by introducing an excess of supporting electrolyte, an excess of inactive supporting electrolyte. Okay. So when the concentration of this supporting electrolyte exceeds 550 to 100-fold, the fraction of the total current carried by the analyte approaches zero. So as a result, the rate of migration of the analyte toward the electrode of opposite charge becomes essentially independent of the applied potential. So yung presence ng supporting analyte prevent migration from happening. Okay, now let's look at the profile. The profiles of this what we call unstirred solution. So how do we interpret this one? So try to imagine we have the what we call electrode system that we have. So what is happening here? What's the reaction? So we have the A plus E or Ne producing a product. So let's assume that A is what? A certain concentration and P is initially 0. And we can also assume that the reduction reaction is rapid and reversible, so that the concentration of A and P, we could say, in the film of solution immediately adjacent to the electrode. And at this time, we can have what? A potential versus the surface concentration as this E applied potent. This is the potential between the working electrode and the reference electrode. E of A, okay, minus 0.0592 over N log CPO CAO minus E reference. So this is potential versus the, we could say, surface concentration or the film of solution that you have there. So initially, what do you have? At 0 time, you apply the potential, and then you hold the potential. Okay. And what happened as you hold the potential? The current that you do initially goes so high, and as you hold the potential, it will go down until you put back the potential to 0. So we could say this is what? Your excitation profile, and this is your response, current response. So once you get it here, the highest potential that you can get the highest current. And then with time, what happened? This one goes down. Why? What happened? So let's try to look at the concentration distance profile. So what is the main mass transfer here? Anyone? Ano sa tingin niyo yung main mass transfer dito? This is unstirred. Wala nang the migration, so it's between what?
Diffusion and convection, sir. So diffusion kasi
Diffusion and convection. So what do you think is the main mass transfer here? This is unstirred.
diffusion,
Wala
sir.
lang, yung nilagay mo lang. So this is more on diffusion. So at the beginning, we could say it's all analyte. At the beginning, there's no product. And if you're going to look from the distance, from the surface, this is what happened. It's all aligned. Now what happened when you start applying the potential? So when you start applying the potential, okay, your product starts to what? Form, right? A plus E giving you P. Now, when the potential goes down, what happened? It goes down there. So we could say A here, your potential here is equals to what? 0 volts. And here we could say E applied is equals to point C. Where's that point C? If we're going to look at the linear thing that we have here, see this? So when you reach the point C, this is what you get. So what happened? Okay. So, ito na yung peak nung tinatawag nating LSC, right? So once you get this, what will happen after 1 millisecond to 5 millisecond, 10 millisecond, your reading goes down. And once it goes down, ano nangyayari? Ganito yung reaction na nagpo-form. Okay? So when you apply the potential, once it reached the limiting current, okay, your concentration that you have there starts to go down. Why? Because the backward reaction is now being favored. Okay? And once it goes down, ang nagpo-form naman is yung analyte, and you have an increase in the concentration of the analyte. So this is, we could say, the profile that you have in an unstirred solution. And later on, I'll show you a real-time data that they have if you have an unstirred solution. Now, how is the profile for the electrodes in stirred solution? How is it different? So this is just a visualization of what? The flow patterns in a flowing stream. So we could say a turbulent flow on the right side, okay, becomes a laminar flow as the average velocity decreases to the left. Okay, so turbulent, laminar. So in the turbulent flow, what can you say about the movement of the molecules? Ano masasabi ninyo? Regular movement ba siya?
Erratic po.
Erratic. Irregular movement, we could say zigzag movement. Okay, there are swirls, okay, in the movement. But in the laminar flow, what do you observe? There's like a streamlines, right? It becomes steady as layers of liquid slide by each other in a regular, what we call manner. Okay, so how do we look at it in terms of the electrode? So we're steering it already, right? So the one in the diffusion layer, the double layer, tingnan nyo yung nangyayari dito, nandoon yung laminar flow of the region compared to this one, which is what? Turbulent. Okay, so I don't know if you see the effect of steering here. Now you have to keep this continuously. So the way you keep this continuously is continuous steering. So the analyte solution is kept in continuous motion. Okay, you can do it by steering the solution or flow solution like the HPLC. Now, if you're going to look at what's happening here, so from the diffusion that is commonly found in unstirred, okay, when you stir the solution, the main mass transfer is now convection. And look at the readings that you have. This is the XYC. Okay. So if we're going to look at this, this is, we could say, the concentration profiles from A producing P. Okay. From a stirred solution. So what's the difference of this? So this is where the initial concentration of your analyte is just equals to 1/2 of the concentration of the analyte. Now compare it to the second one. Okay. So what do you have here? It's the other way around. So if you're going to look from the distance in the electrode, okay, so this should be A and B. So if you're going to look 1, okay, your concentration of the analyte here, XYC, and compare it to the concentration of the product. So initially diffusion, okay, they have a different condition, right? But once convection starts to go in, you see, consistent na yung concentration ng analyte. The same thing here. At the diffusion mode, they have different concentration here. And then once the convection comes in, okay, naging fixed na yung concentration nila. Okay? So That we could say is the advantage of this what we call stirred solution. You can see how it affects the profile. Now, if we're going to compare a data set, so we could say this is what images that shows the LSB of unstirred solution. So yung system na meron ka dito is FeCN 6 3 minus converting to FeCN 6 4 minus. So anong magkakaiba nila? So look at the unstirred here. So 1.3 seconds, 2.08, 2.78. So as you can see, it goes there. Now, if you're going to plot all of them, this is how the plot look like. Now, compare it, same system, but steering. What can you say?
The limiting current, sir, is more prevalent and can be easily measured.
Yep. So ito yung effect na to. And what do you think is the effect here on the diffusion layer? Which one is independent of time and which one is dependent of time? Look what happened here. So after this time, it went down. It just went down. But this one, once you reach this one, you're good. So we could say once you have a steering one, once you reach the limiting current, okay, it can be independent of time. It will be like that. So that's we could say the difference. Now you see the oxidation and the reduction in terms of the color that you have here. So we could say what the effect of steering in the concentration gradient. What does it do? Does steering aids in the analysis? So which one do you prefer to use if you're going to do LSB? The stirred solution or the unstirred solution? Obviously the stirred one. Okay. So that's the one advantage that they have here. But unfortunately, as I have told you, what if you just fabricate your potential stat? Ano gagawin mo? Mano-mano? In those developed, I think, you have a magnetic stirrer. Sabi nga namin, you improvise. Or your, what we call rotating working electrode. It turn around. Umiikot siya. So pag umiikot siya, you're creating like a wave that will steer the whole solution. Okay. And usually when we have LSB, that is a stirred solution. Now, ano naman yung unstirred solution? Anong method yun sa tingin nyo? So in the hydrodynamic, what we call voltammetry, the best example that you have is the stirred one. Now, you can also have a voltammogram of mixture. So like this one. So anong interpretation natin dito? So you look at based on the kinetics of the reaction. So reversible system obey the Nernst equation. So here, if you can get a difference of around 0.1 volt, you can separate a mixture. So we could say this one is what? If you look at the difference between this is 0.1, so we could say at a potential of 0.1 volts, you can get this at a potential of 0.2 volts. You can get this one. So these are just the half-wave potential that differ by 0.1 volts. So you can have a curve A and curve B. So you can separate them. You can also look at in terms of what? This one. The voltammetric behavior of Fe2 and Fe3 in a citrate medium. So the way that you look at this is curve A, it becomes what? Going negative. So this is your anodic wave for a solution, okay, in which the concentration of Fe2 plus is equals to 1 times 10 to the negative 4 molar. Now, how do you differentiate this from the other? Kasi pareho lang sila, right? So this is just what? Why did I call it anodic? Because as you could see here, it becomes oxidized. Now, what happened on the second one? How is this different curve B from curve A? So if you're going to look at this here, when it goes here, this is the one that is formed. So what's the difference between A and B? Anyone? This is reversible. So if this is reversible, you have there an anodic, cathodic wave. And it's happened when the concentration of your CFE2 plus is equals to the CFE3 plus. Now, ano naman to? So this is the one where you continuously applying potential, but this time, this is now all cathodic wave. Kasi production lang yung meron. And the concentration that you have there is just equals to what? The one when you started, 1 times 10 to the negative 4. So you have your equimolar solution of Fe2 plus and Fe3 plus. So depending on the what we call potential that you have here, so you can have some sort of a difference. So you look at the current here. So one is what? Here all negative. You see the difference? The current here are all negative. Here, there's a negative and a positive current. Okay, that's why we call it wave, anodic wave, because all of them are negative. Here, we call it anodic cathodic because you have a negative current and a positive one. But here, all of them are positive current. Now, what happens if you have oxygen and you try to what we call use it in the voltammogram? Okay, you try to what we call reduce oxygen in an air saturated 0.1 molar KCl. So you will see here this peak due to this and this peak due to this one. But if there's no oxygen, what do you see? This one. So how do you achieve this one? Let's say curve B. You remove your oxygen. Okay. And then I told you you have what? The stirred one, right? So what happened if it's the unstirred one? That is where polarography comes in. Okay, so it differs from the hydrodynamic voltammetry because in the first place, this is unstirred, where diffusion dominates. So your dropping mercury electrode is used as a working electrode. So this is what happened. So your mercury is your working electrode. So if there's no mercury there, there's no current that is formed. Now, as mercury is formed there, the higher the mercury until it drops, okay, you're going to get a signal. So once the mercury drops, okay, the current becomes zero again until you start to form a mercury drop. So the current varies as drop grows, then pulls off. Napakasimple nung ano, di ba? Yung principle nito. Oh, sa mercury lang pala. But that makes it also erroneous. Because you want the mercury to be what? Just exposed to the analyte that you want to determine. Okay? Because it can get contaminated and it mess up your analyte. What if in your solution, meron doon yung tinatawag nating mercury binding material? So anong effect nun? You're trying to monitor some analyte in your using mercury dropping electrode, and there's some material or compound in your sample that binds with the mercury, so it mess up the reading. Okay, so the advantage that you have, so this is how you get the signal for this one. It is a clean surface and constant mixing. So the constant current during the graph growth. So there is no hydrogen formation. But the problem with this one is mercury easily oxidized and it's so hard to perform. Okay, when you do this, what we call DME. But once you master it, it's really a good technique. But the thing is, they have to phase out of it because of the hazardous materials of the mercury. So this is the current sample of polarography. So it's still like an LSB. We could say that the two examples of LSB is hydrodynamic voltammetry and the polarography. So if you have a current sample polarography, there's a drop knocker used to detach drop slightly before the natural drop for reproducible drop times. Now, near end of the drop, the current is measured or sampled. The current is held at this value until the next drop. And the sampled polarogram consists of short step with less fluctuations than the reflow. So see how noisy it is? But there's a way to smoothen that to give you that value to this one. You also see this in LC. When do you see this in LC? Anyone? If you remember your chromatography, when do you see your chromatogram to be like that? Anyone? If you use LC, come on. Kapag nagpa-fluctuate yung pressure. So nagpa-fluctuate din yung signal ng chromatogram. Usually what we do here, we have a software, we try to smoothen it. I was like that, and then the professor, why do you need to smooth it? The same thing I told Jeff, bakit mo kailangan i-smooth yan? Kasi maingay daw yung IR. Sabi ko, hindi, talaga maingay siya kasi mababa yung resolution na kinuha namin. So that's what we have for today. And then maybe next meeting we'll do CB. and the other stuff. But I want you to read yung article. Nasaan na ba yun? I try to open. Because I think it's much better if you read it than me telling you what to do. So I would like you to read. Asan na yun? This one. The basics of voltammetry and polarography. So if you're going to look at this. So see where it's similar here. And then what's the other one? Meron ako kasi may hawak ako dito kanina. It's much easier if I show it to you. So, walang background. No, not that one, not that one. Nako, hindi pa rin kita. Here, the one that says basics of voltammogram. Okay. And then the square wave voltammetry. That one. And that one. And then I'll give a quiz that deadlines Tuesday on these materials. Okay, question? Tanong? Now you can see the kitchen. Tanong?